So now let's look at see what happens when both bits are on in our 2-bit R2R digital analog converter. Well, from our circuit, we can convert this into this circuit here. Basically, these 2 bits now, these 2 pins from our microcontroller now have VCC on them. Okay, so our circuit now looks like this. Trying to get V out, we have ground here. And this circuit we can rewrite in this manner. VCC at the top, these are tied together, R1, R2, R3, and R4. Now, just like the situation where we had a digital value of 1, we have a digital value of 3, we basically have something that looks like a voltage divider again, except we have something complicated going on up here on the upper circuit. So we're going to make an equivalent resistance, we're going to call it R upper, that is a combination of these resistors. Now, just like we did for the lower one, we're going to model that as, let's see here, I guess this is an easier way to do that. We're going to model it very simply. We know that R2 and R3 in series become basically R2 plus R3. And so R upper, basically all the resistance here, is R upper equals 1 over R1 plus 1 over R2 plus R3. Now we know from our original circuit that R1 is 2R, R2 is 2R, and R3 is 1R. So we end up with 6/5 R again. Well, that's useful. We've seen this before when we did the lower one. Well, okay, let's go with it. Going back to our circuit, we now know that R upper is equal to 6/5 R. Now, that allows us to figure out what the voltage should be here. Now, just like before, we now have the equivalent of a voltage divider. We have R4 and R upper. And I'm going to call this, now for convenience, the voltage drop across R4. Okay. In other words, from here to here, I'm going to get a voltage drop between this and ground of VR4. Again, this is VCC. Well, we've done this many times before. We know that VR4 is going to equal to VCC times R4 over R upper plus R4, which is equal to, see here, R4 it was 2R over, this here, R upper we calculated as 6/5 R. Again, R4 is 2R. So we're getting, let's see here, calculate this all out, VCC 2R over, that's 16/10 R. Sorry, 16/5 R. So we're going to end up with VCC times 10 over 16, or 5/8 VCC. Okay, so now we know that this voltage here, VR4, is going to be 5/8 VCC. Now going back to our main circuit, let's look at this. We know that VR4 equals 5/8 VCC. So that's right here. Now we got to figure out what the voltage drop is over R3. We can sum that plus VR4 and we're done. Well, fortunately, we've already looked at this circuit. It's here. So we can actually figure out what the voltage should be here. This is just a voltage divider again. Well, that's really convenient. So if we have some Vn coming here, we know that it's going to be some fraction. And in this case, we know that it is VCC on top here. And we know that it's 5/8 VCC here. So basically, the total voltage drop between here and here. So if I was going to measure this, I could say that the V drop over R2, R3 is equal to, let's see here, VCC minus 5/8 VCC is 3/8 VCC. Well, that's convenient. So basically, what we have is now a voltage divider for just this side of the circuit. Here's R2. Here's R3. We know that basically we're getting a drop of 3/8 VCC here. We're going to put this to ground because we're just looking at the drop. We want to calculate what the voltage drop just over R3 is. Well, fortunately, we know that it's just a voltage divider. So 3/8 VCC times R3 over R2 plus R3, which, looking at this, again, we have 3/8 VCC, R3 is R, R2 is 2R, again, R3 is R, so we get basically 3/8 VCC times 1/3, or other words, VCC over 8. Okay, so now, going back to our original circuit, we know that the voltage drop over R4 is 5/8 VCC. The voltage drop over R3 is 1/8 VCC. Excuse me, 8 there. And so the V out equals the voltage drop over R4 plus the voltage drop over R3, which equals 5/8 VCC plus 1/8 VCC, which equals 6/8 VCC or 3/4 VCC. Wow. Okay, that was a lot of work. However, going back to our formula, we see that it predicted that bit 0 is 1 and bit 1 is 1. The digital value is 3, and it predicted that our V out would be 3 times VCC over 4, and that's indeed what we got in the end. Now, the one I didn't do is when the high bit is set to 1 and the low bit is set to 0, but I assure you, if you do the same calculations, we're going to end up with being VCC over 2, and you can do that as a good bit of exercise. Now, this principle that we've done, we've now shown the values we expect out for a 2-bit R2R digital analog converter. You can do all this work and much more to actually do a resistor ladder like this. Or you can get a program to do it for you. There are programs out there that will actually do all these calculations for you. And you find out you get these values as well. But fortunately, somebody in the past has actually sat down and designed this well so you know what the formula should be. So that's a simple digital analog converter circuit. There are other ways to do this. Many different types of digital analog converters. But this is the one that really shows you how to use a resistor ladder.